Hi everyone, welcome to lecture 7. Yes, so today we're going to continue talking about stochastic bandits. And if you recall from the last lecture, I ended the lecture by a brief introduction of a new class of algorithms that not only are applicable in stochastic bandits, they can actually be applied to a large family of Bayesian online optimization problems. And that's Thompson sampling. So I ended the lecture by telling you a little bit about Thompson sampling and two viewpoints about this algorithm. One is a Bayesian viewpoint and the other one is a Frequentist viewpoint. And then I had actually a fun discussion with Mohammad Reza right after the class. I was trying to convince him why Thompson sampling works. And then I realized I actually don't understand well why Thompson sampling works. I have some idea that I had read the paper a few years back. This is a kind of like a beautiful work of Agrawal and Goyal back in, I think the last paper was in 2020 or 2018, one of them. There are some intuitions in the analysis of Thompson sampling, but it's not really like that intuitive. So I decided to sit down and really like learn this analysis and come up with kind of a refined version of what happened in that paper. And that's what happened yesterday. So I'm only a few hours ahead of you in the material that I'm gonna talk about today. And this is why I have a cheat sheet for the first time. And the goal is the following. So I'm gonna basically talk about this algorithm in a simple setting. Stochastic bandits with Bernoulli rewards. So here's the plan. I'm going to give you a little bit of preliminary about an algebraic construct called conjugate priors. If you are familiar with that, then that's great. Otherwise, you will see this kind of like cool. It's a good thing to know when you are thinking about Bayesian optimization problems, so conjugate priors, which actually doesn't have a concrete mathematical definition, but I will tell you the definition that people typically use. Then we're going to talk about Thompson sampling. I'm going to use the abbreviation TS for a stochastic multi-arm bandit special case of Bernoulli rewards. So the first thing is what does the algorithm do? So the description and the formal description of the algorithm. Then we will talk about two ways of viewing this algorithm. Two perspectives. One is the Bayesian perspective, or if you want, you can call it the ex-ante perspective. And the other one is the Frequentist perspective, which you may call it the exposed perspective. And it's going to be clear why I'm calling them ex-ante and exposed, hopefully so. And then we're going to try to analyze this algorithm. So I'm going to go with analyzing Thompson sampling. In order to do that, we're going to follow the two perspectives. So I first going to talk about the Bayesian regrets or ex-ante regret of this algorithm, which I will define formally, and why this is actually small, pretty much close to the information theoretic lower bound, having said that it's not exactly the information theoretic lower bound. There are some follow-up works that they refine Thompson sampling, there are variants of Thompson sampling that achieve the information theoretic lower bound for the Bayesian regrets. But then the good thing is getting the upper bound. It's gonna, I don't know, like half a page. Proof. And this is really like if you understand this proof, then you understand why people came up with Thompson sampling. It comes from a property of this algorithm called probability matching. And I'm going to describe that when I describe the algorithm. And then the rest is just applying concentration. So it's really like at the border of triviality. And then the actual one, frequentist regrets, a little bit more involved. Ten pages with my handwriting, and the actual paper is 21 pages, and the paper is only just like that. At the beginning, it seems intimidating. Has anyone seen the frequentist analysis of Thompson sampling before? Have you seen Shipro's about giving talks on that? Simon's Institute. You saw Shipro's talk, or you have read the paper?
I saw the paper.
Oh yeah, so that one is a monster. No one should teach that paper. It's a beautiful paper, Shipra, but the follow-up that you guys wrote is much better. Actually, the point of the second paper. So it's a much simpler analysis. Actually show that the frequentist regret matches the Leon-Robbins go-around. So this is another algorithm with information theoretically optimal in terms of frequentist regret. And I'm going to talk about not the first paper that Neon was talking about, the second. Okay, let me change colors because this black one is not really readable. 30 questions about the plan. It's a very kind of like concrete plan. And I hope I can cover everything. All right. So let's start from the preliminary that we need for this lecture. We need a couple of concentration bounds, similar to the pack learning bounds that we discussed last time. There is going to be a little bit of refinements to get the right bounds. When we get there, I'm going to tell you what refinements we need. So I'm not going to talk about those in the preliminary. Let me just talk about the conjugate drivers. So this is, let me first tell you what is the conjugate driver involved. Imagine you're trying to estimate a parameter. It's a Bayesian estimation problem. So there's an unknown parameter theta, and then you have observational data about this unknown parameter. You want to estimate that parameter, right? So the one-on-one setting of parameter estimation in Bayesian decision making is the following. Right? So I have this unknown parameter theta, and we assume that theta is drawn from some prior distribution. Let me use, for example, pi of theta to denote the prior distribution. So this is the prior distribution that the decision maker has around this unknown parameter. And now imagine you observe observational data, which are IID samples from some distribution, which depends on theta. So I will have observational IID samples denoted by, say, x1, x2 to xt, which are drawn from some distribution. So I'm going to use these notations of pi of, say, something, conditional theta. This is basically a likelihood function, right? So this is the prior, this is a likelihood function. Given data, you will have observational data. Okay. And then the Bayesian decision maker can always find the posterior, right? So I can think of this as maybe vector x, and then I can always find the posterior distribution, which basically means that, hey, I have some prior belief, I observe this sequence. How would that update my belief about the unknown parameter? So posterior distribution, say pi of theta, condition of the vector x. Let me write it down. So it's going to be basically the prior times the likelihood function at the point x And by the way, so if these are independent IID, then my likelihood function is basically a product distribution. So maybe I can just write it down as the product of the everything. So say this is essentially the product of pi of xi conditional theta, I from 1 to capital T, because of the independence. And then everything divided by pi of x, that you can always write it down as pi of x conditional theta, p theta, d theta. Something like this. This is just basic, right? Now, if you want to have a good algebraic control over this problem, you ideally want to start with, let's say, some family of distribution for the prior. For example, your prior is Gaussian. And then you have a likelihood function, you get observational data. Then once you move to the posterior distribution, you want to stay in the same family. Like for example, if I have a Gaussian distribution as my prior, I see something, I update my belief, and I still remain in the class of Gaussian distribution, but maybe with updated parameters. This is kind of a triumph for the Bayesian decision maker because it gives you an algebraic control over Bayesian updates. Does it make sense? So now this brings me to this definition of conjugate prior. So definition, let's pi, and it's not really a mathematical definition. Because what does it mean that the distribution belongs to a family? That needs to be defined by itself, and I think that's the only part that's not concrete. So let pi belong to a family of distributions. Then we say pi or p is a conjugate prior to the likelihood function p of, let's say, x condition theta. So that's the likelihood function. If the posterior pi of theta condition on x always belongs to same family. Let me give you some examples to make this more clear. Example number 1. Suppose you're trying to estimate the average of a random variable, in particular a Gaussian distribution. So I'm imagining that my theta is drawn from some Gaussian distribution with a given mean and some standard deviation. And now imagine you have observational data that are still Gaussian. So what's their distribution? So they have the same mean as theta, but at different values. So I will have x1, x2, all the way to xt, which are drawn from a Gaussian distribution with mean equal to the unknown parameter theta and some variance sigma 2. So this is the prior theta, this is the likelihood function, and now you're taking out the posterior. So if I observe x1 to xt, what would the posterior on theta look like? So the posterior remains a Gaussian. And Gaussian is actually conjugate prior to Gaussian. The posterior remains Gaussian. In particular, if I look at pi of theta condition on the vector x, then this is going to be normally distributed with some mean and some variance. They have it. one of those things that you should always Wikipedia. I know this fact from probably like 2010, and still I can't memorize it. Actually, Mohammed, very nicely print that cheat sheets. It's going to be normal with mean mu 0 divided by sigma 0 squared, which is the effect of the prior, and then this is the effect of the observation. Summation xi, and this is the effect of the light. Times 1 over n divided by sigma squared plus 1 over sigma 0 squared. So that's the new mean. And the new standard deviation is, or variance is 1 over sigma 0 squared plus n over sigma squared to the power minus. It might look complicated, but at the same time, it's much simpler than if you had gone outside of the family. So the only thing that we need to update the knowing summation of x. First of all, the variance has nothing to do with the observation. The variance is fixed for the posterior. And then the mean depends on the observation in kind of a linear fashion, right? So if you look at the summation of xi's, these are all, this is a linear function, right? There's a linear function as a function of summation of xi that tells you what the mean is, and then the variance is fixed. And you only need to look at now this distribution of the posterior. Okay. Yes.
Somehow related to just doing a linear regression. It should relate because in the linear regression, if we assume we have like a normal error.
Right. So the best linear regressor is the maximum likelihood estimation estimator. Right. The map estimator. It's the maximum posterior distribution, but in some sense, if, for example, you assume your likelihood function is uniform, well, so here it's not here. So it's going to be map. So in that sense, this object will help you to identify the best linear regressor.
Right. It's probably the mean.
And I agree with you that somehow the map should depend. Well, so and then for the posterior distribution, when you think about the peak, right? So the peak is mode is equal to the mean.
Right.
So I guess in that sense, the point that maximizes your likelihood function is linear function. So I agree with you that if you run a maximum likelihood estimator, then this is going to be your estimator. For map, you need to multiply that by the prior. I think it gives you the same thing. Good. Yes. So I think one way of looking at this is a separator of your points somehow. Or a linear interpolation that has your points. So example number 2, which is the one that I'm going to use today. Let me write it down here. One of the things I'm practicing is being more efficient in using whiteboard. I'm actually pretty bad at that. And I only realized it when I was watching the recordings of the lectures that space is not being used efficiently. Let me try to do that in this lecture. So the second one is about basically Bernoulli trial. So you observe Bernoulli trial from an unknown mean, and you want to estimate the mean from the Bernoulli trials. So now imagine theta is drawn from beta distribution. And beta is this weird distribution where PDF is, we're not going to use all of the things I'm writing down here. Just for the completeness, so the PDF is going to be x to the power alpha minus 1 minus x to the power beta minus 1 divided by gamma alpha, gamma beta. So gamma is the gamma function, which is the continuous extension of factorial function, divided by gamma of alpha plus beta. So this thing is in the denominator. That's the PDF. They have two parameters, alpha and beta, and somehow we should think of alpha as the parameter that is positively correlated with C more number of ones in the Bernoulli trial, and beta is positively correlated with C more number of zeros in the Bernoulli trial. And to make this a statement more formal, if we assume x1 to xt are basically Bernoullis, 0, 1 Bernoullis, with parameter theta under IID, then what happens is that the posterior remains a beta distribution. The posterior remains a beta distribution. And actually, this time, the update is pretty easy. So all you need to do is count the number of ones that you see in this capital T number of trials and number of zeros, which is T minus that. And then increase alpha by that number, by the number of ones, and increase beta by the number of zeros. So P of theta condition on the vector x would be basically beta distribution with updated parameters. So alpha plus summation from 1 to capital T, indicator that xt was equal to 1. So it's the total number of ones plus beta, and then the second parameter is beta plus summation T from 1 to capital T, indicator that xt is equal to 0. And this is quite nice. Right. Let me tell you one nice fact about beta distribution, which actually comes from this observation, and you're going to prove it in your assignment. Fact. Try to get the facts right. You're going to use that in. It's a very cute thing. So. One minus, so let's say f of beta with parameters alpha and beta is the CDF of beta distribution. It's parameters alpha and beta. Then if I look at the probability that, let's say, beta distribution parameter alpha and beta is larger than some y, the random variable from that distribution is larger than 1, I claim this is exactly equal to, let me write it down, f of binomial distribution. Right, when I look at alpha plus beta minus 1 trials, and the probability of each trial being 1 is equal to y. And then I want the number of trials to be smaller than alpha minus. Number of ones in the trial to be smaller than alpha minus. See the assignment. Hint. Use example 2. So this is going to be handy when you're thinking about table bounds on beta distribution, and that's basically the only thing I will use about beta distribution in the lecture. Probably is the only thing I will use. But yeah, so there is a long list of, by the way, conjugate priors. for discrete distributions and continuous distribution, I encourage everyone to check the Wikipedia page. It has 2 large tables. You can look at that, and maybe some of them will be helpful at some point in the future. Any questions?
Just quick question, if the conjugate property doesn't hold, can we, see if we can still estimate the posterior, right?
For sure. This is why I say it's an algebraic construct. It's just gonna help you to analyze things easier because you have a closed form for the posterior distribution. Otherwise, you're absolutely right. So Bayesian updating is always valid. Red, but my red is the best. So now this brings me to Thompson sampling. So the way that Thompson sampling works is actually working in a kind of in a Bayesian environment where as a Bayesian decision maker, so you have, let's say, n Bernoulli arms, which unknown means, mean rewards are unknown. And then you have a prior over those mean rewards. So Bayesian environments. For multi-arm bandits, for stochastic multi-arm bandits. It's exactly as before, so I'm going to assume that there is a prior distribution for each arm. For arm J, and really think of it as the prior over the mean, and this is important. Keep that in mind throughout the lecture. Every time I'm talking about this prior and posteriors, they are not about the rewards. They're about the mean of the distribution from which the rewards are generated. This is the slippery slope. So if you start thinking about this problem that every time I'm saying posterior, or you say Rod is talking about the reward distribution and the posterior of the reward, then you go through a rabbit hole that you will lose. We will kind of like stop understanding what's happening in this lecture. So every time I talked about prior distribution or the posterior distribution, I really am referring to the mean of the distribution from which the reward is generated. Okay? It's very important. Prior distribution of J for arm J, and because this is the distribution for the mean, that means mu J at time 0, let's say, is drawn from this prior distribution. And what is mu J? So now, once these mu's are generated independently across arms, and it's important, so for every, so the mu J are independent across arms. Let me not overload the notation across arms. Now, once these prior distributions, once these means are drawn from the prior distribution, you have an instance of the stochastic multi-arm bandit like before. There will be capital T number of rounds of decision making, and rewards are going to be IAC. So for every arm J, RJT would be drawn from, let's say, a Bernoulli distribution, because I'm taking a Bayesian environment for multi-arm bandit, but restricted to Bernoulli rewards, the Bernoulli distribution with mean mu J. And now the setup should resemble the estimation problem I was talking about. So this is the prior, this is the likelihood function from which the rewards are generated. And your observational data when we pull an arm is really like the reward of that. Does it make sense? Good. And now you have a decision maker that knows the prior, let's say, or you can assume that doesn't know the prior. There are 2 setups. If for the sake of this lecture, let's assume the decision maker for now knows the prior. So you know the prior, and you start putting these arms, and your goal is to minimize regret. But let's define the benchmark. So benchmark, and this benchmark is important to define carefully. So the benchmark I star is going to be the arm that maximizes my mean reward. So argmax mu J over all J's in N. So the setup is we have n arms. I'm not going to rewrite it again. So n arms, capital D number of rounds. The rewards are going to be Bernoulli's, as I wrote down. And this is going to be the maximum arm, right? Because, well, so you have an instance of a stochastic bandit. So this guy is going to be the guy that if you put it in every single round, it gives you the maximum expected regret condition on the realized means, right? So the important thing to note that this is now a random variable, right? Because mu's are drawn from a prior distribution. So therefore, the arm that maximizes things is going to be a random variable, which depends on the prior. And this is actually quite important. Now, I can think of the regrets. And defining the regret depends on which stage of this game you're looking at. If you're looking at the game at the exposed stage, after the mu's are drawn, this is basically a stochastic multi-arm bandit, but you only tie the hands of the adversary that picked the mean reverse to pick them from a prior distribution. Right? That's the only definition.
Because you are using likelihood as a Bernoulli, do you assume that the prior is better or?
For now, no. In the definition of the Bayesian variant, you don't have to. But when you're designing an algorithm,
Also, the algorithm needs that.
it doesn't need that, but in order to be able to write it down, describe the algorithm and describe the analysis in 3 hours, I think they'll need Yeah, so I will encourage you to read 10 part-out papers that I wrote down on this topic to say the algorithm is actually oblivious to the choice of the prior, the analysis also is oblivious to the choice of prior, but it's very complicated. Now, in terms of regret, so one stage is exposed when mu's are drawn. The other one is ex-ante regret, which people also call it Bayesian regret, which is basically the regret bound before the arms are drawn in expectation. So I'm going to take another expectation over mu's. And this is important because, well, so your optimal arm is not going to be fixed anymore. It depends on mu. So therefore, I'm taking another expectation. Even opt is going to be a random variable that you're taking the expectation of. And you should expect, so okay, if I'm designing an algorithm, which of these two objectives are harder? Exposed regret or ex-ante regret? So if I have an algorithm that has a small exposed regret, does it imply a small ex-ante regret as well? Or is there any kind of connection with that too? If you think about it, exposed is basically for every sample path of mu, you can get a small regret with respect to I star. If I manage to do a good job in every single sample path, then the expectation I'm also going to do a good job. Therefore, having an algorithm that has a small exposed regrets or frequentist regrets would result in an algorithm that has a small Bayesian or ex-ante regrets, but not the other way. So I could just focus on the frequentist exposed regret for the sake of this lecture and show you the Thompson sampling that I'm going to describe soon. We'll have exposed regret that is small. But just for the sake of understanding why on earth people even think about Thompson sampling, I'm going to actually show you a simple analysis of Bayesian regret of Thompson sampling. But disclaimer, in some sense it is redundant because if you have a control over the exposed regret of any algorithm, including Thompson sampling, you automatically have a control over the ex-ante regrets for the Bayesian. So let me define those. So okay, so I'm gonna define, let's say, the exposed regrets of the algorithm to be a random variable. So it's gonna be t times mu of I star minus summation t from 1 to capital T mu of IT. And you might wonder, well, so this is random variables in many ways, but I'm also taking some expectations. I'm taking expectations the conditional way on the reward, so therefore I'm replacing R with mu. I think my students in this class have seen this trick so many times that I don't want to just like write it down in the form of like random variable take expectation. So really think of it as this is a still a random variable because there is randomness in mu. There is also randomness in the decisions of the algorithm if you run a randomized algorithm. But rather than that, I'm actually taking the conditional expectation at every single time on the rewards, the actual realization of the rewards, that will give me mu's rather than r's. But rather than that, everything else can be written like this way. Okay? You can call it pseudo regret if you feel like that, but it's really like regret random variable after carefully bringing down the conditional expectation every single round, condition of the path, and then only taking expectation over the randomness in the reward and leaving the rest as random variables. Okay. And then ex-ante regret, or the Bayesian regret, is basically the expectation of this thing when you withdraw from F. Let me write it down. It's going to be the expectation of summation t from 1 to capital T, mu I star minus mu I.
F is the distribution, the true distribution.
It's the ground truth distribution, the prior distribution from which mu's are drawn. Therefore, I can take expectation over that. Now, for a second, let's say you want to minimize this quantity. You don't care about x plus 3 good, you want to minimize this quantity. What would you do? Can you actually design an algorithm that is distribution condition on the past at every single time is exactly equal to the distribution of the R late picks is exactly equal to the distribution of the R minus? Is there any smart way that you design an algorithm that at every single time is drawing an R, and then the distribution over R that induces condition of the history is exactly equal to the distribution of the optimal R? Because if you do that, then it seems you're doing a pretty good job. Condition in the past, your distribution is the same as ISR. I'm not saying condition in the past and condition on mu. That's too good to be true. If condition in the past and condition on the mu, you could get an algorithm that had the same distribution between IT and ISR, then your regret level is 0. But let's say I'm just conditioning on the history, all the observational data that you receive from pulling the R, but I'm leaving mu as a random variable. Can you design an algorithm that gives you the same distribution over R? Seems a little bit tricky, yes.
You mean distribution of IT across empirical distribution of IT across?
No. For every single time t, I want the following. So the probability that IT is equal to I, condition on the history up to that time, and this probability includes the randomness in mu, to be equal to the probability that I star is equal to I condition. And I want this to be exactly equal for every single time. It's called probability matching. I mean, Bayesian decision making, this is actually a common trick. And if you achieve something like that, then roughly speaking, it seems well, so at least condition in the past, these two guys have the same distribution. So if mu, for example, was deterministic, if you had a point mass, then I would have received 0 regret. But of course, mu is not point mass. If mu was a point mass and mu f, then that was equivalent of knowing mu. Problem was trivial at the first place. So you don't know, it's not a point mass, it's just some distribution. But for any distribution, can you actually do that? And that's Thompson sampling. So Thompson sampling is probability matching, and I think it's going to be elaborate.
Can I have a question?
Yes.
I'm stuck in something. So X post is X post after realizing mu J, or the samples from the Bernoulli variables?
No, so expose is basically expected regret that your algorithm gets in the induced stochastic multi-arm manifold once mu is realized. So imagine previously this was if mu was known, this was the regret that you were studying. Right?
If mu was Bernoulli, I'm not convinced that this is mathematically correct, that this is equation. Because this IT can be path
This is definition.
but this is path
But then there is also actual regret that you can get. And then the point is, if you can make this quantity small, then the expected regret that you can get can also get small. Condition mu. So now if you want your proof, so imagine I'm doing the fact. I'm looking at the expectation. For now, let's say I'm taking a condition on mu, right? So t mu I star minus summation t from 1 to capital T R of IT, right? That's I think your concern that I have a regard. And I'm conditioning on mu. I can write it down as the following. So t times, so it's going to be t times expectation of mu I star condition on mu minus, now we can say summation t from 1 to capital T expectation. There is expectation also outside. I'm going to tell you. So it's actually a triple expectation. So mathematically, I don't need this is wrong notation. No mathematician should do that. It's not mathematically well defined. And let me actually be very precise about expectations. Expectations are expectations. So expectation summation t from 1 to capital T, expectation of RIT actually time t condition on ft minus 1. And I have another expectation here. But then the outer expectation is condition. The condition mu, these are independent type of star drawn from the Bernoulli. So then this is going to be mu IT. Then you can collapse everything. So my point is, if you manage to make this small, then your expected regret would be condition mu would become small. And that's why I'm defining exposed regret. That's kind of, did that come in?
we can talk about it. Maybe I'm just confused.
But do you see what's happening here?
Yeah, I
What's ft minus 1?
That's the history of the time t minus 1.
I think the notation might be like that because like you said fj is
Yes. Okay, let me use h. Thank you.
So
You're describing, so it is important to treat my notation. Thank you.
okay, that's fine.
So what is the question there?
My question is different. So I didn't understand your question when you say it can be designed an algorithm that isn't that by definition? So whatever we had done, so I star is gonna have some distribution across the arm,
Right.
and then we choose IT.
Right.
And same.
So what would be that algorithm?
So isn't this the oh, you mean
How we can construct that algorithm? Do you want to calculate the distribution drawn on from it, or
no? I guess it's gonna be you count
no?
how many
it's gonna be
arms
sample
this
sample.
bond.
It's going to be exactly sample sample. So because you keep track of the posterior distribution, you sample and then you take max, so this has the 10 distribution of max.
Oh.
Just wait.
I think I know what to ask. So that mu IT is a random variable based on the history.
Based on no, so that's the point. So if I condition on ht minus 1, then it is not a random variable.
Yes, but taking expectation of mu IT.
But well, so the randomness at time t is independent from it. The condition in the history, randomness of the reward at time t, randomness in the likelihood function is independent from your IT. Therefore, this becomes mu. And then you can just use the law of expectation.
Okay, let's talk about this one.
I'm just using basic definition of expectation. We can chat. This is not the first time I'm actually doing this. This is the fifth time I'm actually doing this. If you, so you don't agree with the definition of pseudo-regression and stochastic planning? You think that's not a well-defined definition? Because it's a gap, right? So it's gap times the number of times that you put your arms. I think you're a little bit. Let's chat offline. I don't want to confuse you further. You look like a question mark. All right. So Mohammed Raza is absolutely right that there is an algorithm that does that, but then the algorithm, one way of describing that is through Thompson sampling. The Thompson sampling. I'm going to restrict my attention to the Bayesian environment where my prior distribution is beta, so that I can have a good algebraic control over the posterior distribution. So now imagine the problem I want to solve is the Bayesian environment with beta prior and Bernoulli remarks. Okay. So now first Thompson sampling is going to say, hey, I'm going to set two parameters, alpha and beta, to be, say, 1 and 1. I don't think it is really important how you initialize. Then I'm going to set the prior for Rj to be equal to beta distribution with parameters alpha and beta. And you do that independent alpha j and beta j. So you're keeping track of one alpha beta for every R. And now, from time 1 to capital T, here's what I'm going to do. This is the interesting part. So I have some distribution. So again, these are distributions on the means, not the realized rewards. So I sample from them, and these samples are not representative of the reward. These are the representative of the mean of the arm. So I'm going to take samples, draw J, T, say, from Fj for every j in N. So now you have one representative for each arm, which is a sample from the posterior, from the current, say, posterior distribution for this guy.
So here you're not playing any arm, right? You just sample.
I'm just going to play an arm. So who arm IT, which is going to be the arm that maximizes PJT, J in N. I'm drawing these samples from the posterior distribution, the current posterior distribution, and full arm IT. Now you observe the reward for this arm, and this is crucial in the algorithm. So you only observe the reward for this arm. So as a Bayesian decision maker, only the posterior or the prior distribution, or let's say the current posterior for arm IT should get updated. And I'm going to do it. So I'm going to say f of j is going to remain the same. It's going to be called f of j, but every j that is not IT. And then for this guy, f of IT is now going to be a beta distribution again. Why? Because beta is a conjugate prior to Bernoulli. And then my parameters are going to change. So alpha is going to be increased if RIT is equal to 1, and otherwise beta is going to increase, beta j, beta IT. If RIT is 0. And then we continue. Right. Now, think of a Bayesian decision maker for a second. So there is a ground truth for my mean rewards, which I'm drawing from that in the algorithm. And then I'm doing a proper consistent Bayesian updating using Bayesian. I'm keeping this posterior distribution, so they're really like honest posterior distribution for all the arms. And then somehow you want to sample from ISR. What would you do at every time t? If I condition the past, all I can do is that, well, so ISR is the maximum arm, and I already know the conditional distribution from which the rewards are, the means are going to be realized. When I get into this rabbit hole sometimes, the means are realized, and the maximum arm is the arm that has the maximum mean. So let me just take a sample and look at the maximum. Then condition on the history, this will have exactly the same distribution as the maximum. And that's the probability matching problem. It's one smart way of simulating in a conditional fashion the actual output. Right? So Thompson sampling has that property by construction. And let's see how we can use that property. And it is important that this probability is only conditional in history, so there is randomness involved in the priority. Yes.
So the reason for drawing PJT is for exploration, because I know the mean of the distributions per arm, right?
So there are different viewpoints about why do you want to do that.
Yeah.
So you're right. So you know the means, so you can take the expectation and go with the maximum.
Yeah.
So that's equivalent of kind of like greedy algorithm. So in that sense, you're absolutely right that you want to have some exploration. The way I think about that is this. So if you go with the maximum arm that has a maximum expectation, this is not going to match the probability.
And yeah, why is this critical? Because even if I don't match exactly,
Yes.
I have like a bias estimator, and if I manage to reduce it, I should be fine, right?
I mean, I can't argue with you that if you don't match it, then there will be no hope in the
Right.
future. But this makes sense that you want to match the probability because, in some sense, this is pushing you towards zero regret. Not even a small regret, like zero regret. In the special case that mu is deterministic and you knew mu, it's a trivial problem, but if you had that, then this will exactly
Kind of enforce like concentration inequality in every.
and then your intuition. So this is gonna in the unconditional world, when you are looking at the ex-ante regret, it's gonna be combined with the concentration on the lane concentration, and that gives you small regret bound for ex-ante stage. And this is what I'm going to show you. Right. Erase this part of the whiteboard. The Bayesian regret of Thompson sampling. Let's just write it down. And this is a test for understanding conditional expectations and the law of iterative expectation, the linearity of expectation. And then the rest is going to be kind of tricky. So I'm going to write it down as, hey, I'm looking at the expectation mu drawn from F, summation T from 1 to capital T, mu I star minus mu I T. So I'm now not be a good mathematician and use the incorrect notation of expectation with respect to a certain random variable. Just bear with me for a second. So mu run from F, and then I'm going to look at summation. So the expectation of summation T from 1 to capital T, expectation of mu I star minus mu I, condition on mu IT, condition on HT minus 1. So that's a new notation for history of society. And here we go. Yes.
Is that kind of also translates to correlation gap or something? Do you know any connection with that?
I'm not sure. Okay. So for just question number 1, is it 0? Because ISR and IT in conditional history, they seem to have the same distribution. So if I take expectation, is it 0? No. Do you want to explain more as why?
I think that we are kind of fixing the distribution that IT is getting ex ante, but I star is kind of in every realization is the maximum, so in every realization fix the best. That was kind of my intuition for correlation gap. So maybe, yeah.
Maybe coupling is a better word. There is a smart coupling of the two algorithms that will give you a good figure. So Mohammad Reza's point in one sentence is mu is a stochastic. If ISR and IT they have conditional HT minus 1, they have the same distribution, then that doesn't make this 0. Because I'm not taking the expectation over right. So I guess what I wanted to do conditional mu. Right. So if I'm conditional mu, then they don't have the same distribution. Okay, does it make sense? The condition mu and history of that time, then these two they don't have the same distribution. But now you can do a smart trick. So let me do the fun. So I'm gonna try to compare this algorithm with UC. And for that, let me define the UCB of arm I at time t, which we defined last time. So it's going to be the mu hat of I up to time t minus 1 plus the Hackney term. I hope I won't make a mistake, log 2 over delta divided by n I t minus 1. And I guess the way I think about that this is the empirical average. I'm using notations from last time, so it's the empirical average from all the pools up to time t minus 1. This is the number of pools that you have received. And delta, this little delta here is basically the probability, guard probability that you are targeting. And I'm using the pack learning route. Great. And then I define this event E to be, or event EI to be the event that essentially mu I minus mu I hat t minus 1 in absolute value is smaller than that log 2 over delta divided by nit minus 1. And then condition on mu, so I know that the probability that EI complement happens, condition on mu is smaller than delta for a given I for a given t. That's how we defined the pack learning bound last time. Is it do you guys see what I'm talking about? Like I'm referring to the confidence bounds that we defined last time, the pack learning bounds, and if you are looking at the event that you land in the confidence interval, which is equivalent of what I wrote down here, the probability is going to be delta if you set the confidence interval length to be twice of this quantity. And then, therefore, I'm sorry. So let's look at this comment. So therefore, the probability of there exists an I such that EI complement happens, or in other words, the union of these guys, union of EI complements, and then we actually call this EIT. It's a better notation. So over all I and all time t would be at most delta n times t. And you should really think of delta as something like 1 over t squared so that you make this probability small. So therefore, the probability that for every I we have for every I and t we have EIT would be at least 1 minus delta nt. And somehow I'm looking at the situation when these events happen. So that means the averages, empirical averages, and the real means are close to each other. But then I can do the following trick, and that will essentially change the correct assessment is what I have. Because I use this notation. Now, if I want to write it down, I would say this is the following. So this is going to be, just in parentheses, so this is going to be equal to the outer expectation over mu. And then I have this other expectation. And then some t from 1 to capital T, expectation of mu I star. I'm going to subtract UCB of arm IT at time t and add the same quantity, UCB of arm IT at time t minus mu IT. So this is conditional history of time t minus 1. And then I have this outer expectation. The point is, if I condition history of the time t minus 1, then what happens is that this quantity, the UCB, is going to be determined because mu hat is going to be determined, therefore mu hat plus this thing is going to be determined. So now that I have probability matching, I can say, well, so here I can replace IT with I star. Because you have this property, then you take expectation over everything, right? So this is the expectation of IT equal to indicator of IT equal to I condition. C is equal to the expectation of I star equal to I condition B state. So therefore I can say, hey, so there is an randomness here, that's fine. We can always take expectation over that. The part that was important was about IT, and condition on FT minus 1, there is no randomness in this class. Because I'm conditioning on observational data, who cares what was the prior distribution? It's just the actual numbers that matter. So this is going to be deterministic. So therefore, this is going to be equal to the expectation of mu drawn from F, expectation of t from 1 to capital T, expectation of mu I star minus UCB of I star plus UCB of IT minus mu IT, conditional history. And now you should have a guess where is this going. So for any arm regarding of either a stochastic arm or a deterministic arm decided by the algorithm, decided by the Bayesian optimal benchmark, etc., we always know that these two quantities are close to each other. And So, for example, we know it is going to be negative, right? So if the good event happens, then mu I star is always smaller than u c of I star. It's true for every single r at every single time. So this is going to be negative. And then this guy is not going to be negative, but it's going to be bound by some quantity. Okay, so let me call this whole thing gamma. So first of all, expectation of gamma condition on, let me call this event E for E good. So gamma condition on E good complement is bounded by what? Like a maximum thing that this quantity can get. So it is something like T, I believe, 2T. If everything is bounded, there's a 0, 0, 1 numbers, right? So everything here is going to be between 0 and 1, but this whole thing is divided by 2T. And therefore, the expectation of gamma indicator of E bar good, when the complement of the good event happens, would be at most 2 delta n t squared. And if we set delta to be a small, let's say 1 over t squared, then you're kind of like okay with this part of the expected result. What about the expectation of gamma when and bear with me, so this is expected gamma. So gamma is a random variable. So gamma is like this whole thing that's happening. The expectation of gamma condition on the good events. Now I claim this is at most. So first of all, this is going to be negative, so I'm going to get rid of these parts. So it's going to be this term. So it will be at most expectation of mu drawn from F. Expectation summation T from 1 to capital T. And condition on the history, so we know that, and the good event happening, so we know this is going to be bounded by that term. So it's going to be bounded by, let me write it down. So it's going to be summation I from 1 to n, indicator that IT is equal to I. And then if IT is equal to I, this one is going to be upper bounded by log 2 over delta divided by NIT. Does that make sense? This is basically upper bounded. And now, if you focus on each arm, I, for example, so I guess this can be written down in the following way. So it's going to be expectation of mu drawn from F, expectation of summation I from 1 to n. And now I'm looking at only arm I. So this arm at some point is going to be pulled once, then it's going to be pulled twice, it's going to be pulled 3 times, all the way to Ni capital T. So then this summation that you see here is essentially equal to summation, say, k from 1 to NIT. And every time the term that you're adding up is going to be the square root of log 2 over delta divided by k. Does it make sense? So you're adding up all these terms. Every time that, so look at now all the terms corresponding to arm I. So for those, you have a square root of log 2 over delta divided by 1. And then a square root of log 2 over delta divided by 2. And this goes all the way to Ni capital T. So these are contributions of arm I, and then you have to add up over all arms. And then this is going to be, okay, so this summation is basically upper bounded by the integral from 0 to Ni capital T of 1 over the square root of SDS. The whole thing multiplied by square root of log 2 over delta, which is equal to 2 square root of Ni capital T times log 2 over delta. Therefore, I can say this whole thing is upper bounded by, let me write it down up there. So this is star. The star is upper bounded by just one expectation of I from 1 to n. Times the square root of log 2 over delta MIT. And now log is a concave function, right? So this is, sorry, a square root is a concave function. And then I'm going to use So you're looking at the summation of a bunch of a square root of a bunch of things. So you can divide by 1 over n, multiply by n. And then say this is advanced expectation of n times 2 square root of n times 2 the square root of log 2 over delta. I'm breaking the other terms out. And then you have the square root of summation NIT divided by n. Summation of NIT is the total arm force at all times, which is exactly equal to T. This is equal to T. So this is going to be now square root of 2. Let me bring it inside. It's going to be something like 4 NT log of 2 over delta. And I'm going to set delta to be, let's say, 1 over T squared. And knowing that capital T is the larger number of arms, so this is going to be order square root of NT log T. And then the other term is going to be order n, which is smaller than that, assuming, again, T is smaller than n. So therefore, expected ex-ante regress is going to be bounded by order square root n. The two terms, one is the one that I calculated, the other one is 2 delta nt, but then assuming that delta is equal to 1 over T squared, this is just going to be order n. And T is larger than n, so this is a dominating term, so you get order square root n y. Okay. So a little bit more than half a page, but pretty much just a concentration now. So let's have a break for 10 minutes. You're gonna continue at 10:30, and I'm gonna show you how to do the frequentist analysis of Thompson sampling. But this is, I think, a very intuitive analysis, and it should kind of make it clear why people think about Thompson sampling, why probability matching is a good property, and how probability matching translates into Bayesian splits. Yeah. All right. So let's try to continue. All right, so we're going to go over the harder part of the analysis, which is the frequentist regress. So the recap, frequencies or exposed regrets. So what we're going to show is that for every mu in the support of and the following quantity is response. The regrets exposed, which is really a function of mu implicitly defined as t times mu I star minus summation t from 1 to capital T mu I t. This is a swap. All right. And then we know that we can always write this down as summation I from 1 to n mu I star minus mu I, which is what we call gap, times ni capital T, and ni capital T, the recap, or ni little t, is taking the total number of pools of arm I up to time t, including ts.
I guess Parv's point.
Let's take that offline.
No, I mean, we cannot make that small. We should take expectation over randomness of algorithm and the history.
Algorithm is deterministic.
And the realization of the sample path. If realization of the sample path is random, we should take expectation of that over the realization. And that's what we can say is gonna be a small, right? If we don't take expectation, we cannot say for every realized sample path we can get a very small.
Right. So
that was Parv's point.
So I'm going to take an expectation over these with only respect to the randomness in the algorithm. And we are talking about Thompson sampling, which is actually a randomized algorithm. So I take it back. It's not deterministic. And yes, so we're taking expectation over that randomness, the randomness in the poster. So you sample the PJT.
The sample. Also.
Right. So I'm going to take expectation over that.
That and also the realization of the sample path, but not the.
What do you mean by the realization?
The reward.
That's already taken care of. They're mu's. They're not ours.
No, but
IT depends on the reward, right? IT, because you update the posterior based on the reward. So IT depends on how the reward.
Right, but if I condition with the history, this is the calculation. This is why we take this offline. Can we take this offline? Because I already showed you proof over there, and you didn't pay attention. Now you're asking me. All right. So NIT is the number of rounds T prime is smaller than T. Just the summation T prime from 1 to T indicates there that IT prime is equal to I. So total number of rounds that you take that. So what I'm going to show you is the following. So I'm essentially going to look at the quantity expectation of NIT, where this expectation is taken over the randomness of the Thompson sampling model.
sorry.
Yeah. Reminders are always better. So I'm going to look at this quantity. I try to actually bound this quantity. Okay. And this is this disclaimer. I have some intuition what's going on in this analysis, but I think it's really a complicated analysis in many ways. And this is why the frequentist analysis of Thompson sampling was open for a while, for a lot of years, maybe for at least 15 years. So the analysis is involved, and I think not only is involved, it's very clever. in several ways. So I will try to tell you some of the ideas and intuition behind that, but I don't think I have fully digested everything that is happening. So some parts are going to be algebraic. I will try to give you intuition, but there is a limit to which I can do. So for this particular track, so this can be written down in the following. So it's going to be summation t from 1 to capital T, and then I'm looking at the probability that at time t, my algorithm is picking I. And if you add up those probabilities, this is going to be the expected answer. So here is the geometric picture I would like you to think about. So suppose I'm keeping track of the posterior distribution of the needs, right? It's like some distribution, whatever it looks like. So this is going to be the posterior distribution. And then throughout the analysis, you need to keep track of two quantities. One is the average empirical mean of each arm. So it's the posterior distribution of arm J. I'm going to keep track of mu hat JT minus 1. That's the empirical mean, just average mean. And then the second quantity is PJT, which is the sample from the posterior distribution that you have. And then I'm going to look at two specific thresholds. So let's say this is so let's say this is the actual mu J. And imagine this is a suboptimal arm. So J is not equal to J star. But mu J is somewhere, right? So you have this posterior distribution, the expectation will give you the correct quantity. And it's going to be somewhere. And then there is this other quantity, which is mu J star, which should be larger than mu J. So this is, let's say, mu J star. I'm going to look at two barriers between the two. So let's call the first barrier number xj. These are deterministic numbers in some way. Condition mu, so the other one is yj. And what are these barriers? So these barriers are somehow designed in a way that they are between mu j and mu j star. And then they satisfy the following two properties. So xj and yj such that first and second. The first one is the following. So if I look at the callback labor divergence of xj and mu j star, this is pretty close to the callback labor divergence of mu j and mu j star. But by a factor of 1 plus epsilon for a given epsilon. So fix some epsilon greater or equal than 0. And then x and yj, which are not parameters that the algorithm uses, these are parameters I'm actually using my analysis, are designed such that, first of all, this is true. And second, the callback labor divergence of xj and yj is equal to callback labor divergence of xj and mu j star divided by 1 plus epsilon, and therefore is equal to the callback labor divergence of mu j and mu j star divided by 1 plus epsilon squared. So xj and yj, the amount of closeness that they have kind of is depending on how close mu j and mu j star are. So if mu j and mu j star are pretty close, xj and yj are going to be close. Somehow xj is close to both yj and so it is closer to mu j than mu j star, and same as yj. So yj is kind of like closer to mu j star than mu j. And then the separations are in the following. And if you're wondering why callback divergence is important, this goes back to the Leon-Robinson that I was talking about last time, that any arm under any algorithm, as long as it gets sub polynomial time regret, should be put in expectation at least log t divided by the callback labor divergence of uj and uj star. And these set of parameters are somehow related to that, but very, very mysterious at this point. Now I'm going to use this xj and yj to kind of separate these events. I'm going to say this is equal to the summation t from 1 to capital T, probability that it is equal to I. And it happens that mu hat j t minus 1, your average empirical set of that point is larger than xj, plus the probability that it is equal to I, and mu hat j t minus 1 is smaller than xj, but then pjt turns out to be larger than yj. And then finally, the probability that it is equal to I, and then somehow both the average mean and the sample mean are not very far from, they don't overshoot them. So until now, nothing fancy. Now I'm going to show you basically all of these terms are somehow small. That's kind of like the analysis. And let me not follow my notes. I should start with the simpler ones. I'm going to call this guy 1. Or let's say the whole thing 1. I'm going to call this guy 2. And I'm going to call this guy 3. Let me analysis. Cooper sketch. Or various sketch of the proof. Found 1 and 2 and 3 setup. So let's start from one of them, which actually you already should be able to found, and that's 1. So founding 1. And for that end, let me remind you. We talked about Chernow-found last time. Let me tell you a refined version of Chernow-found, which goes by the name of Chernow Hofstee found. And it's going to be helpful in bounding the term 1. So let x1, x2 to x capital T be Bernoulli with the same probability. So Bernoulli probability, say P. So they are in actual Chernow-found, we're just assuming that x1 to x3 were independent, bounded, so they are yes.
J there is same as I.
J is same as I. What does that mean?
Summation, we are IT equal to I,
Oh,
but the
and this
other ones
is-
are J. Shouldn't that be JT equal to J?
I am sorry. So this is correct. So this is J.
All of I's are J.
Yeah, so this let me change
Yeah.
these ones. Sorry, you're right. That notation. I use J in my notes. I use I in the previous one. Yeah.
Okay.
Thank you.
Yeah.
Good. Right, so let's say these guys are a Bernoulli parameter P. Now, here is the concentration boundary density. So the probability that 1/t summation xt t from 1 to capital T, which is something in expectation equal to P, is greater or equal than P plus epsilon, would be a smaller than e to the power minus T, and then I look at the divergence, the callback labor divergence of P plus epsilon and P. Somehow the right exponent when you look at IID Bernoulli's for the channel bound is actually a callback labor divergence, callback labor divergence of the two quantities, the modified mean and the actual. And if I look at the probability that 1/t summation T from 1 to capital T xt is smaller than P minus epsilon, and this is also going to be at most e to the power minus T, the divergence of P minus epsilon. So I'm going to use this channel bound. This is very standard. We can the proof exactly follow the same lines as channel bound, just look at the moment generating function of Bernoulli's, and that automatically gives you this once you optimize the right hand side of the bound. Exactly the way that you typically approach it. So I'm going to use this bound. And now I can say the following. So imagine I'm looking at term 1, so it's a summation T from 1 to capital T, probability that IT is equal to J. And mu hat, which is the empirical average of the time T minus 1 is larger than xj. Then this can be written in the following way. So this is basically at most a 1 for the first time that you pull the arm. And then I can look at all the rounds that this arm J was pulled. We saw similar argument before when we were taking the Bayesian regret. So I'm going to look at K from 1 to T minus 1. So this is so K equal to 1 is the first time that this arm J was pulled, K equal to 2 is the second time it was pulled, and the maximum time it gets pulled can be T minus 1 at most. And then every time that it gets pulled, I'm looking at the probability of this event, right? So probability that mu J hat at time tau J K, and then define this time, is greater than xj. So what is tau Jk? So imagine tau Jk is defined to be the time in 1 to t such that J is pulled for the K study. Right? Does it make sense? Because I'm looking at one particular arm J. So here you only have one term every time that the arm being pulled is J, and then you can go over the index of outputs, right? The number of outputs. 1, 2, all the way to T minus 1, and every time you're just adding up these terms. But then we are looking at the average of Bernoulli, so we can use general Hopsing bound. and say this is at most 1 plus summation k from 1 to t minus 1 e to the minus, because there were k folds, right? So it's t is equal to, as if t is equal to k, so k times the divergence, callback divergence of xj and actual uj. And then actually write this as summation. So this is at most summation k from 0 to infinity of e to the minus k callback divergence of xj and mu j. And therefore, this is going to be equal to 1 over 1 minus e to the minus k, so e to the minus divergence callback labor xj mu j, because it's a geometric sum. And this is at most 1 over callback labor divergence of xj and mu j. Why? Because I'm using the fact that 1 minus e to the minus x is greater or equal than x. Or sorry, let me do it properly. It's not in the other way. But this is almost x up to lower order term, so it's going to be this plus order x squared, and I'm just getting rid of the lower order terms. Now, what do we know about this quantity? Based on the definition of x, so we know this is 1 plus epsilon, right? Divided by the callback labor divergence of mu j. Actually, I want this to be x. Let's keep it like that. So the point is, this is a constant that is gap dependent constant. I'm gonna get back to this term later. So I might need to change the definition of xj and yj. Somehow in my notes, we can just call this a gap dependent constant. And the reason I'm calling it gap dependent constant is because it's not a scaling t, right? So it is quantity that only depends on the gap of mu j and mu j and so on, the way that you define xj and yj. So if I give you some xj and yj that satisfies these two, then you can always write down some gap, some form for this quantity, right? But it only depends on delta j. Is it clear what I'm trying to say? So this is an instance dependent constant. Does not escape it. By proper choice of xj. Xj is a number, yj is a number. These numbers are defined based on the parameters of the problem. So this is going to be a gap dependent or instance dependent constant. Yes.
And yj was defined there. So why we are saying here Bernoulli identity? Where you are using
This is little x. Again, another bad notation. So in the constant. I'm sorry. We should stop it. So this is little x is that little x yj, the barriers I had in the analysis. These are the Bernoullis. So my
how
Bernoullis are
come
going to
here-
rewards. So there's a number. So it's like summation of Bernoulli, which are the rewards, divided by the number of rewards, reiterated at most is greater than the barrier xj, so these are numbers. This x is not that x. This is little x and capital X. That's for the random variable, but this is just a dependency function.
You had it's just simply summation of the river.
The average, the average, so empirical average. So there are certain rounds that you put this R, you get to the bar, you take the average. All right, so this was kind of easy. The first term is a good term, so it gives you a constant. And it should be expected because somehow this is saying that, hey, I'm looking at the rounds in which there is a large deviation between the empirical mean and that guy. So either you don't pull this arm that often, and then this term does not appear that many times, or if you pull it so many times, then it should get smaller and smaller. And in fact, it's going to be a geometric series. So sum of two constants. Let me switch to the second term. Using the board more efficiently. For the second term, this is actually interesting. So I'm looking at summation, so second term. And we get the summation t from 1 to capital T. Probability that IT is equal to J and mu has this time is not overshooting that much, so it is going to be a smaller than its own corresponding barrier xj. But then the sample mean that you have in Thompson sampling is overshooting. And you should expect this is not also a very likely event. But the question is it going to be constant? Is it going to have another dependency on t? And it turns out that this is actually the term that gives rise to Leigh-Robbins lower bound. So this has log dependencies. And let's actually see that. So this is going to be at most. So we need careful conditioning on upper bounding, summation t from 1 to capital T. So I'm going to condition on the event that mu hat jt minus 1 is smaller than xj. So you can write this probability as a probability of this and that, condition on this times the probability of this event. And then I can just bound that second probability by 1. So I can say this is upper bounded by sum from t from 1 to capital T, probability that IT is equal to j, and the overshoot on the sample happens if T is larger than yj, condition on mu hat jt minus 1 is smaller than xj. And let's think about this for a second. Well, this is actually one step of the answer that I have with the equation that's happening. So we are saying, hey, the empirical mean was smaller than xj. So for a second, imagine if xj and yj are exactly equal to mu j. So it says, or let's say xj and yj are, right, so let's say they're smaller than mu j. So they're equal to mu j, just some number. So this says, the empirical average, actually, not assume xj is equal to mu j, but yj is slightly larger than mu j, so there is a gap between xj and yj. And then you're looking at the event that your empirical mean could get things right, but then your sample was off. But then you should expect that if the sample from the posterior distribution is off, the empirical mean should be also off and vice versa. So this event shouldn't be very likely. In other words, the fact that mu j had t minus 1 is smaller than xj, this is saying something about the number of bonds that you had. It says the number of bonds that you had in the sequence is at most xj times the number of times that you put this on. And then remember, so we are keeping track of this beta distribution that are posterior. So the fact that you don't have that many bonds in your pool so far should somehow say something about the current distribution that you're facing, the posterior distribution. And for such a distribution, you should not get a sample with a very likely probability that is larger than yj, because yj and xj are far from each other somehow. Especially if mu j and mu j star, if the arm is very suboptimal, then their distance is even going to be more. So let's try to quantize it. I'm going to say this is always upper bounded by, for any integer m. So we upper bounded by, let's bring out the first m term in this summation and just upper bound the probability by 1. And then I'm looking at the remaining. So the first non-zero, let's imagine. So every time that you're putting anything rather than j, here you have a 0. Every time that you pull rj, you have a 1. So the first m1 of them, bring them out and upper bound that by 1. Now you're in a situation that you have pulled this r at least m times. Okay, so I'm gonna now look at time t from, I had that definition over there, so tau j and m plus 1 all the way to t. Probability that it is equal to j and ejt is larger than yj, condition on mu hat jt minus 1 is smaller than h. And you can write down this probability as the expectation of the indicator. Let me do that a little differently over there. So I can erase this part, right? So I had it in my notes, so we know what is the third event. And the third event is actually the tricky one. Yeah, I really like this stuff of the analysis, the one that I'm going to show you. I think it's the most intuitive stuff. Right, okay, so let me say it in, let me write it down first, and then I'm going to say it in words. So so whatever I had here, call it star. Star is equal to, so we are going to use that nested expectation trick again. So summation expectation of summation t from tau j n plus 1 to capital T. And then I'm looking at the probability that it is equal to j and pjt is equal to yj, conditional history of the time t minus 1, and the event that mu hat jt minus 1 is smaller than xj. And this is actually kind of a funny conditioning. Let me tell you why. Because if I condition on the history up to time t minus 1, so I'm conditioning on all the observational data I received in my R groups, then you can calculate mu hat jt minus 1 and see whether it is smaller than xj or not. So essentially what I'm doing is I'm conditioning on all those histories that are consistent with this condition. That's called consistent conditioning, yes.
We cannot compute xj, so that
Compute xj?
you said
xj is a given number. What do you mean we cannot compute?
the algorithm doesn't.
I'm analyzing
That's
that.
right.
I'm analyzing that. So I think in the analysis, I'm just conditioning on consistent history with this. Like look at all the sample paths, condition on those sample paths in which this condition was satisfied. That's the mathematical meaning of this this type of conditioning. And then you start seeing what's happening. So what's happening is that, so I can write it down, upper bound further by I'm going to get rid of this part, which is okay. Expectation of t from tau j m plus 1 to capital T, just the probability of this event. Probability of the event that PJT does the overshoot, while I'm looking at the history in which mu hat JT minus 1 was a smaller than this. So we know our posteriors are going to be beta distributions. I'm looking at the probability that PJT, the sample I have from the posterior distribution, is larger than YJ. So I'm kind of like looking at 1 minus CDF of the posterior at that round. But what we know about the posterior is that up to that point, this event happened, right? Let's focus on this event. But if it is the case that mu hat j t minus 1 is smaller than some number xj, that's equivalent of saying, hey, the total number of arm pulls that you have for these cars was less than x. It's equivalent of saying that number of bonds, summation t from 1 to tau from 1 to tau from 1 to nj t minus 1 indicator that the realized reward at time tau was equal to 1. So this is just the total number of bonds that you get is smaller than n j t minus 1 times xj. Right? And we know our posterior is going to be a beta distribution with parameters. The initial alpha was 1, the initial beta was 1. So 1 is going to be added to that for the alpha part, and then njt minus this is going to be added to 1 for the beta part. But now here's a funny fact. So if I have the fact about beta distribution, fact, if I look at beta distribution with parameter alpha and beta versus beta distribution with parameter alpha prime and beta prime, where alpha is greater or equal than alpha prime, somehow the posterior is indicating it's more likely to have a 1 here versus there, and beta is smaller than beta prime, then you can say beta, alpha, and beta is stochastically dominating beta, alpha prime, and beta prime. And first order? First order. Because I care about CDS. So. And in other words, if I know the number of bonds I have is smaller than njt minus 1 times xj, I can say the probability that I am larger than yj is at most the probability that the beta distribution where alpha is equal to that and beta is equal to whatever it should be is larger than yj. So in other words, this is going to be just this term, the probability that PJT is larger than YJ, condition of the history up to that time, and mu hat JT minus 1 to be smaller than XJ, which is equivalent of you have bonds that is smaller than, right? Important. So this guy is going to be dominated by the beta distribution where the number of bonds you observe is equal to njt minus 1 times xj. So this is going to be at most 1 minus CDF of beta distribution at the point yj, where my parameters are alpha and beta. Alpha is equal to 1 plus xj times njt minus 1. And beta is actually equal to njt minus 1 times 1 minus xj. Let's think about this step of analysis again. What I'm saying is that, hey, I'm trying to upper bound this, right? And when you think about this step of the analysis, PJT is drawn from the posterior distribution that has a beta distribution, part of the family of beta distribution. So how many ones I have seen, how many zeros I have seen for this arm to find the parameters of the corresponding beta distribution. So I know that if I'm conditioning on those sample paths in which mu hat jt minus 1 is smaller than xj, the number of ones I have seen is smaller than this quantity. And therefore, the number of zeros I have seen is going to be at least nj t minus 1 minus this quantity, which is nj t minus 1 times 1 minus xj. Starting from 1, 1, it's going to bring me to this beta distribution, but this is not exactly the distribution I have. It is only stochastically dominated, it's only stochastically dominating my distribution. Therefore, the probability that I'm greater than yj would be at most the probability that that guy that is stochastically dominating me is smaller than, is at least yj. That's 1 minus CDF of beta of alpha and beta, when alpha is 1 plus xj and j minus 1. Beta is nj t minus 1 times 1 minus xj. Is this a step clear? So I'm using the information I have about the empirical average up to that point to say something about the posterior distribution. I'm saying if the empirical average, this is really critical. Right? So knowing that the empirical average is small says something about the number of bonds that you received. And number of bonds that you receive tells you what is the posterior distribution. So if the number of bonds that you receive is smaller than, for example, the number of times that you pull the arm times xj, I think it's xj, the fraction of the times that you pull the arm is smaller than, a fraction of times that you pull the arm and you got a 1 is smaller than xj, then your posterior can't be anything better than this. In terms of the stochastic, first order stochastic dominance, yes.
I'm not gonna use that binomial.
And I'm going to use that binomial thing here, exactly. So I'm going to use the other fact that I showed at the beginning about connection between binomial and beta. So this is going to be equal to the CDF of binomial distribution when the number of trials is alpha plus beta minus 1. And the probability of having a success in the trial is equal to yj. And I'm evaluating the binomial at alpha minus 1 there because I don't want to have more than alpha minus 1 successes. You need to show this fact, and this is part of your assignment. Is it there? All right, and then, all right, so another property of binomial is that this quantity I don't know if I should write it down. If you're familiar with asymptotic equipartition property in information theory, this is basically saying that let's say I have some number of Bernoullis, the success probability is equal to P, then most of the, right, so if I look at the most likely sequences that I'm going to see, and the last, so you have you have n rounds, and then each Bernoulli is going to be 1 equal to P, if I look at most likely sequences, and the most likely sequences are those that they have around NP number of ones and N times 1 minus P number of zeros. So if you look at the total mass on these likely scenarios, then this is going to be around 2 to the minus N times binary entropy of P. Okay, so that is this inequality. I'm going to write it down. This is not only at most, it is actually in the limit when t goes to infinity exact, then we at most e to the minus this alpha plus beta minus 1, which is nj t minus 1 actually, times the callback labor divergence of xj and yj. Yes. It's an upper bound and tail of the binomial distribution. And in fact, the upper bound comes from fixing the mean fixed and letting the number of trials to go to infinity. In that case, in the asymptotic, you're going to have this tail bound, which is e to the minus the number of trials times the callback limit divergence of the actual mean and the point that you're looking at. If you look at alpha minus 1, alpha minus 1 is xj times nj t minus 1. So this is why you have xj here, and yj is the actual probability of the underlying sequence of Bernoulli trials. Yeah, so the assignment that you will have is showing this fact and this information theoretic fact. The basic fact from information theory. And if you haven't taken any course in information theory or you haven't read the Thomas Cover's book, I strongly encourage everyone to at least read a few chapters there to make yourself familiar with many of these information theoretic tools. They happen to be helpful in many, many areas, including machine learning theory. All right. So we are getting there. Now I have this bound. I can say, well, putting everything together, the bound that we want to get to is upper bounded by. So we have this m, and then we had each term like that is going to be upper bounded by e to the minus njt minus 1. And these nj's, again, because I'm only looking at, I should have not dropped this. I should have not dropped this. I'm so sorry, guys. It's like a little bit more subtle. I just realized that. As I said, I'm a few hours ahead of you. Yes, so I'm not dropping that part. But I'm upper bounding this second term. Sorry, I'm not dropping it there, but here I'm actually just upper bounding this term. And then this can be written down as the probability of this condition that times the probability that it is equal to j condition the rest. So this part is going to be upper bounded by this term. This other term is going to be upper bounded by, let me write it down. So everything is going to be upper bounded by summation e from tau jm plus 1 to capital T. And I have the indicator that it is equal to j. Right. And then the other term, when you take the expectation inside, is going to be upper bounded by e to the minus nj t minus 1 times the callback label divergence of xj and yj. Okay, and this is what you're trying to bound. So again, you only need to look at the rounds in which njt gets updated. So it's going to be upper bounded by m plus k from m to infinity, because we know at least m number of rounds the R has been pulled. That's the definition of tau jm. And then in any of those rounds, I'm going to get e to the minus k times the callback label divergence of xj and yj. Right? Give me a second, and then we can actually go over all the way to t. It should be t. Now let m to be the following quantity. It's going to be log t divided by the callback label divergence of xj and yj. If I do that, then every term here, therefore, if k is greater or equal than m, you can say e to the minus k callback label divergence of xj and yj would be at most one over t. So by this choice, it's going to be upper bounded by log t divided by callback label divergence of xj and yj plus this summation k from m to capital T. Everything is bounded by 1 over t, so this is just at most 1. So it's going to be at most 1 plus log t divided by callback label divergence of xj and yj. And by the choice of xj and yj I had at the beginning, this is going to be 1 plus epsilon squared for the given parameter epsilon that is used in the analysis times log t divided by callback label divergence of mu j and mu j. And this is exactly the term that appears in the Robin's law. Was this part clear? So shooting this m is a trick that you use in the analysis. So this is true for any m. If you pick m equal to this quantity, then this term becomes a constant, and then you get this bound by the choice of xj and yj is upper bounded by 1 plus epsilon squared divided by callback label divergence of mu j and mu j. Yeah.
I mean, but if you choose m equal to 1, do you agree that that thing is gonna just get smaller because e to the power of minus something is less than 1? So m equal to 1 is the best choice for that. And then again, same trick as the bound 1 that you did in the previous board. You could drop off the log t term and just get 1 divided by callback label divergence of x and y. So the log t term will be dropped.
No, but I'm not following.
So it's a geometric sequence again. So you
Get
are
up to t.
from 1 to take it to infinity. Take it to infinity, so k equal to 1 to infinity, exactly same as the previous board. So we will get that thing is gonna be 1 divided by 1 minus e to the power of minus callback divergence, which was also found. And the log t term will be solved. Choosing m greater than is just solved.
Over a good point.
For those two facts, we don't need the number of samples to be large, right? The two facts that change.
For the first fact, no. For the second one, I don't think you need that because it's again a stochastic dynamics. So that's a very good point.
So maybe the log term appears because of the other.
No, actually, the other one is a constant.
The improved them.
If it says m equal to 1, then I think is that you don't know the J and J are. That's the
Maybe we can
great
discuss
question.
offline.
I think I see what's happening. I see. Yes, I think the bug is the following. So I'm sorry that you have to go through this. So here's the bug. When I added this, I think I was wrong. My note was correct. So here in this step, it's going to be equal to, it's going to be greater or equal than. I'm going to drop this and. The reason I'm dropping this and is because if I get the project in condition of that, then I'm not sure. Right, so good, because if I look at these two and I want to separate the two events, then I have to look at the property that JT is larger than Yj, condition on IT is equal to J and the history multiplied by the other probability. So if you apply Bayes' rule here, then you don't get this term. Actually, you get this term condition on all these events together with IT equal to J. And condition on IT equal to J, the distribution is going to be different. So the posterior is not going to be beta anymore. And that's important because your algorithm already selected J. So here I'm just going to drop this there. Then this is going to be upper bounded by this term still. Now I don't have this indicator anymore. Because I don't have this indicator, I'm going to only bound this by T itself. It's going to be upper bounded by T basically from 1 to capital T. And I will have a T here, or T minus 1.
Not T, NJ.
No, but that's the point. I don't have any bound on NJ. I'm adding up all around, including those that NJ is
But
not
that's
being
tricky
put.
because NJ can remain fixed. So the exponent
Right.
shouldn't go smaller and smaller. So you should add up
No,
all.
so what happens is, NJ is constant for some time, and
Okay.
then it's gonna go up, and then constant go up.
Exactly. So the exponent should remain NJ, but you should sum over all.
Right, I get my point is like, the only thing I can think is I can't bound NJ by T or anything. That's the only thing I can say.
Yeah.
Because NJ is gonna be at least M. And now you need this trace. Now M should be log T over that. Because this is not a geometric series anymore. So it's like add summation of a bunch of terms, are gonna make everything to be 1 over T, and therefore you get. So the part that I made a mistake, not in my notes, but on the whiteboard, was that I included this event. But if you include that event, then you don't get this term out of it. You get the term which is the probability of PJT is larger than YJ, condition on everything here, and IT is equal to J. If you condition that, then the posterior distribution doesn't remain to be beta. Sorry about the confusion. Let me give you some time to fix your notes. Thanks, Mohammed. That was a very good catch. Right. And then the interesting part is these are the easiest steps of the analysis. The actual key lemma that they use, which is novel, and I'm going to show you in a second, is for bounding the third term. In some sense, these were straightforward. I agree that these were straightforward to analyze. So this third one, I don't even have an intuition where it's coming from. But the idea is that we are trying to, we are focusing on the probability of the event that IT is equal to J. And mu hat JT minus 1 does not do an overshoot. And your sample mean doesn't do an overshoot. And you should expect that this is a small. This is what they're saying. So the key part of the analysis is showing this number for the bad arm or a suboptimal arm. And then we write down the lemma. The lemma, which is the lemma, is actually quite nice, is trying to connect this event to the event that optimal arm is being used. So imagine the same event, but rather than J, I'm looking at optimal arm. So probability that IT is equal to J, and you had JT minus 1 is smaller than XJ, and PJT is at most by J. It says that at most 1 minus, let me use this notation alpha JT divided by alpha JT times the probability that IT is equal to I star, and you have JT minus 1 is smaller than XJ, and PJT is smaller than YJ. And alpha JT is defined to be the probability that the sample from the optimal arm is indeed larger than YJ, condition the history up to that point. the key lemma somehow connecting this term with the probability that at that same time I star has been proved, and says I think the crux of the analysis is that then I can only focus on the round in which I star was proved, and I add up these terms, and then we show that this summation is not that. Yes.
Those remain J, or those should also be I star?
J.
Alright, so that's not the same type of term.
No. It's just like exactly the same probability under the same condition, but only assume that the optimal arm was. So we're going to get back to the one. I will try to show you why this is true. But let's see why this lemma is actually helpful. And that part is easy. And then I'm going to get back and tell you why that lemma is true. We are getting closer to the point of the analysis that I think it's not just someone who was really smart came up with a very novel analysis of an algorithm. If you have intuition, I think everyone would be happy to hear. As I'm explaining, if you could build up some intuitions, let me know. I have a good intuition about how to bound 1 and 2 and why we are using those cases. But for the third case, when this event happens, I don't have a good intuition what is happening. So let's try to use the lemma for now and try to get a bound. So we are looking at summation t from 1 to capital T, probability that it is equal to j, and then you don't have an overshoot. So mu hat j t minus 1 is smaller than xj. And the overshoot not only does not happen for the empirical mean, but also the sample mean does not overshoot. And then we're going to use the same trick as before. So we're going to write this down as expectation of some t from 1 to capital T. And I'm going to condition on the history up to that point. So probability that it is equal to j and mu here it is extremely important to condition on the history of that. That's the lemma. Right here we have also the condition on the history. Right, so no condition on the history as before. Then we have the other expectation. This is the same trick as before. Now I'm going to use the lemma, so it's going to be upper bounded by expectation, summation t from 1 to capital T, probability that it is actually equal to the optimal arm, and you have j t minus 1 is smaller than xj, and pj t is smaller than yj. The one important observation is the following. So if I look at arm J, during the epoch in which there is no new draw from arm J, neither of the two quantities change. So mu hat J remains the same. At the same time, the distribution from which Pj is realized is going to remain the same. Right? So therefore, I can write this thing in the following equivalent way. So it's going to be equal to summation t from 1 to, let me write it down and then I will explain.
Isn't there a 1 minus alpha?
Yes, you're right. I missed that term. So 1 minus alpha j t divided by alpha j t, that comes from them. Yes. Yes, you're right. And this times that condition on history of the 20. All right, so this is now upper bounded by, or actually equal to, summation k from 0 to t minus 1. So I'm looking at epochs in which arm j is being put. So k equal to 0 is the 0th time, and then we have first time and the second time, let's say all the way to t minus 1. It's going to be actually an upper bound. And then in all of those epochs, importantly, alpha jt remains the same. Why is that? Because alpha jt is the probability that optimal arm is larger than yj. Right? And anytime that is the case, right? So I'm looking at the epochs corresponding to optimal arm, right? So because this is what I care about. So every time that optimal arm is being pulled, this distribution gets updated, alpha jt, because alpha jt is the quantity that depends on the distribution of the sampled mean from optimal arm. But then between those epochs is the same quantity. So therefore, it's going to be summation k from 0 to t minus 1, and then I'm going to write it down in the following ways. There's going to be expectation of 1 minus alpha j tau of I star and k plus 1 divided by alpha j and tau I star k plus 1 multiplied by t from tau I star and k plus 1 all the way to tau I star and k plus 1. There's k plus 1, and then there's k plus 1. And then I'm looking at the indicator that it is equal to I star and mu hat j t minus 1 is smaller than xj, and pjt is smaller than yj. All right. So what are these taus? Just as the recap, so tau of I star and k is the time when arm I star is being pulled for the k time. Therefore, I'm summing up k from 0 to t minus 1. So I'm going over different pools of arm I star throughout the process. And then between any two pools, this quantity, 1 minus alpha jt divided by alpha jt remains the same because the distribution of the sample mean from optimal arm remains the same. And that quantity only depends on that distribution. This will come out. And then you have this summation after. So important is this summation is at most 1, right? Because there will be only one pool of arm I star during that time. Happens at the beginning. And now we are kind of like upper bounding everything with kind of a nice term. So it's going to be upper bounded by summation k from 0 to t minus 1, expectation of this quantity. 1 minus alpha j, tau of I star, k plus 1, all the way to alpha j, divided by alpha j, tau of I star, and k plus 1. Okay. And I think at this point I can give you a little bit of intuition what's happening here. So this alpha j tau I star k, so what does that mean? So that means I'm pulling arm I star and I'm looking at the probability that that arm is larger than yj. So remember, so if xj and yj's, this is the picture you should have in mind. So you had mu j here. For that mu j, I had this xj and yj, and then I have mu star. So these barriers are decided kind of in a smart way, so that if I, for example, look at the events, after enough number of pools from arm I star, for example, if I look at the pi star t, the sample from a distribution, the probability is larger than yj, it should be pretty close to 1. Because that sample is very likely to be around mu star. Okay, or in other words, this probability, as you pull arm I star more and more, it should get closer and closer to 1. Right? And when you look at this, this is 1 over that probability minus 1. So if the difference of that probability with 1 somehow geometrically fast converges to 1, converges to 0, then you're in a good shape. So let me reiterate the intuition here. Using this magic lemma, which I don't have any intuition, what it does, I have some, but not really like really intuitions. We can relate the term 3 in the analysis to these terms, just a straightforward algebraically using lemma 1. And then these terms are interesting because it's kind of like summing up bunch of 1 minus probability, 1 over a probability minus 1s, or say 1 minus the probability divided by the probability itself. And these probabilities, as you get more and more sample of arm I star, they converge to 1. If the convergence happens fast at an exponential rate, then you should expect that this summation is a constant. And this is exactly what they show in the paper. And by the way, so when you think about this, if you want to like pull off the rest of this analysis for this step, this is kind of like a straightforward calculation, right? Because I know how many pools of the arm I star I have, right? So that's k. So given some number of pools of arm I star, then with the beta prior, you should be able to calculate this quantity. It's going to be very messy. So this part of the paper took them 8 pages to find a proper bound on this. And just like to say that at this point, it's just pure algebra. Because you know the distribution, the posterior distribution, that's a better distribution. You know how many times that arm has been moved. Therefore, you should be able to really like write down this term. And then the rest is upper bounding that term. So I'm not gonna show you that step. I refer to this lemma in Agrawal and Goyal. Just a very messy calculation. I won't even write the exact lemma. I'm just gonna write a version of the lemma that we've been out. So lemma in the Agrawal and Goyal paper, 2020. So they say there exists instance dependent constants such that the expectation of 1 over alpha j tau I star and k plus 1 minus 1, which is the term that we're talking about, is going to be at most. So some instance dependent constant C1 if k is smaller than another instance dependent constant C2. And then it's going to be up to lower order term, something like C4 e to the power minus e to the power minus C5 times k plus C6 and e to the minus C7k plus C8 e to the minus C9k. So there are actually 3 types of exponential functions appearing here. K is larger than C2.
C3. Sorry, C3.
I keep C3 hard. We have started with C3 and then make my life hard. 7. All right, so 8 pages of calculation, but again, I'm going to emphasize. So this step is nothing smart. It's just a straightforward calculating this term, and you actually have closed form for these expectations. You can just write it down and see what the boundaries are. And then by some algebraic manipulations, you get this upper bound, and then the bottom line is these are exponential functions. So when you add them up, then you get geometric series. So therefore, the summation of these terms would be another constant dependent, instance dependent constant. It's going to be another instance dependent constant. Which is really nice. Yeah.
Then when you are taking out that 1 minus alpha divided by alpha, when you're epoching things, you're essentially conditioning on the fact that you don't take I star, right? So you take that out. But that means that then you cannot use a simple indicator function to say expected of that indicator is equal to P, because
sorry, I'm not following. So what I'm doing is I'm dividing time into those epochs, and then in all of those epochs, the distribution of my sample mean from the I star remains the same, the distribution. And therefore I can bring that out for every epoch. And then what do I have inside the epoch is just this random value. Right? So I'm not doing anything, I'm not conditioning, I'm just saying during that epoch the distribution remains the same. So therefore this term, these are the distributions.
Why the expectation over that indicator becomes that coefficient of probability there? Because that probability
I could write everything as the expectation of the indicator. Of the expectation of indicator.
and then
Condition
on the epoch,
on-
right? And then you have that. Right.
And then I look at the epochs, and then
Okay.
during each epoch, the distribution of the sample from the optimal arm remains the same,
Okay.
and therefore that comes on. All right. Cool. The only thing that is left, so that you have actually seen the full analysis of Frequentist analysis of Thompson sampling, which is, I think, an nice achievement, because I personally have never attended the class in which they could teach it. Maybe it's not very teachable as you partially saw. The only step left is proving this lemma. And the proof is not difficult. It's clever, but it's not difficult. It's actually straightforward to some extent. And therefore, I'm going to leave it as an assignment. So you will see in your assignment how to prove the scope of the analysis. And in order to be able to pull off this, you need to have a good understanding of conditional expectation, how it interplays with samples that you draw from both the optimal arm and the original arm. But the rest is just, this is really clean. And I think when you see a nice paper that cracks a longest standing open problem, usually there is this core lemma. And those core lemmas are clean and straightforward exposed once you see that, but before seeing it is really not clear that this is the lemma that you need. So if you are looking for that core technical component in Agrawal Goyal paper, then so it's really like the key lemma that make the analysis novel and very interesting. All right, so let me conclude. Sorry that it was a little bit shaky. I'm apologizing from the person who is describing today. I'm happy to share my handwritten notes if that helps. But yeah, so part of this is me trying to understand the paper and trying to come up with some simpler steps. I think what we saw for group of 1 and 2 is a little different from Agrawal and Goyal. I tried to understand what was happening, so I came up with it's the same thing under the hood, but just polished version of what's happening in that paper. But this third step is I followed literally everything in that paper because to this day I'm not able to digest what's happening here. All right, hopefully you can. And let me know if you have a better intuition or you have a good understanding of what's happening in the last step of the analysis. So just one thing before we leave, actually 2 things. Thompson sampling, one reason it is very powerful is that even though we talked about the stochastic bandit, you can actually think about any sequential decision-making problem when you're Bayesian and there is some underlying unknown parameter. So then you can assume there is a prior on that parameter, you have observational data, right? Try to form posteriors, and then using the posteriors, do the probability matching. So in this context, probability matching was equivalent of sampling from the posterior distribution and then going with the maximum sample. But in other problems, it might be a different operation, but you can always do the probability matching. And there is a Bayesian analysis of Thompson sampling for Bayesian framework that follows the same lines of argument that I had for Bayesian analysis of regret of Thompson sampling. And this is basically, as long as you can do probability matching, you can have results in very, very general settings. It doesn't need to be bandit problems, it can be contextual bandit, it can be reinforcement learning. Like for example, there is a version of Thompson sampling that works in reinforcement learning and bounding the Bayesian regret in that very general problem is literally the same line of arguments, it's just probability matching has a different form. So next time that you saw something about Thompson sampling, it wasn't multi-arm bandit, try to identify whether it is a form of probability matching or they do something really. All right, and then the second thing, we have guest lecturers next week. 2 of our principal researchers, Yu-Yang Zhang and Yiding Feng. They're sitting over there and here. They're going to present their recent papers on online learning and sampling. So one paper is about online learning and queuing. The other one is about online learning and information design. So we are going to learn some basics of queuing, some basics of information design, and how they interplay with online learning. And thanks to you, Yang and Yiding for willing to get lecture next week. Yes.
We have 2 more lectures. Yeah, one next week and one.
Yeah. So let's talk about that. I'm not sure. Yeah. So we need to find a time for a makeup lecture, or we can just call it a day and say 8 lectures is enough. I'm happy to have the 9th lecture because I was planning to talk about either incentivizing exploration or dynamic pricing, and I couldn't talk about that in the given time. I was going to actually talk about Yiding's paper and Yu-Yang's paper, and then I realized they're sitting in the audience, and why should I not ask them to present, and I present the result to them. So this is not the best way of using the workload. So happy to have that, but then, yeah, so there are 2 topics. One of them is something I can cover in an extra lecture. So one thing I can do is I share the notes with you guys so that you read offline, or we can have another extra class. Because I owe you one class. Anyways, let's make that decision next time, all right? You can. Thank you. I'm sure.